So now, yeah. So I'm very excited to do this talk about recursive fish inside a fish. This is a picture of a woodcutting by Escher. It's called Square Limit, and you can see it has all these beautiful fish sort of recursively getting smaller and smaller into infinity or something like that. And in this talk, we're going to try to sort of live code something that looks similar to this, at least in structure. And how can we do that? Well, I'm missing one image. Where did he go? So this is Peter Henderson, and without him, I couldn't do this talk. So in 1982, he wrote a paper called Functional Geometry, and he sort of, in that paper, he gave a decomposition of this image and showed how you can sort of reconstruct that using functional programming. And I'm going to try to do the same now today in 20 minutes in Elm. Wish me luck. Okay. I'm not an Elm programmer, by the way, so to add to the suspense. Okay, so this is a fish. Can you see the fish? So this is my reproduction of the fish that Henderson used in his paper. Yeah, and it's an SVG, and it's a Elm creates the SVG. Let's see. So I have my Elm code here, and it's very sort of rudimentary and simple. Can you read it? Is it too small? Should I can probably increase the font size. Something like this might be better. Okay, so what we have? Well, we have a box and we have a fish. So I should show the box. So this is the box. Sort of interesting thing in Henderson's paper is that a picture is not what you might suppose. A picture is not this. This is a rendering of the picture. The picture is a function that takes a box and produces a rendering. And we can sort of type that nicely in Elm as, you know, a picture is a function that takes a box and gives you a rendering. And a rendering, what is a rendering? It's a, well, you can't see it because I'm shadowing it. It's a list of shapes and styles, but we're not going to really worry about that. That's our SVG. But we will worry about this, and maybe we should worry about what a box is. So a box is these three vectors. So it's an A vector that points from the origin up here, and it's a B vector that sort of stretches out there, and it's a C vector that goes up like that. And when I say that a picture sort of adapts to the box, let's see how that works in practice. So I can change my box, right? So if I change it like this, I'm going to change just the vectors. Let's see. I don't know. Now what happens to my fish? Well, it's still the same picture, but it looks different because I gave it a different box to sort of adapt to. Now what can I do with something like that? I'm just going to use the original box again. Well, it means I can sort of create transformations for my picture just by manipulating the box. So let's see. I'm going to do something like this. Is this correct? Yeah. No, it's not. So I'm just changing the box. And if I move the A vector as well, it looks better. So now I sort of rotated my picture, but what I really did was change the box. So I'm going to exploit that to create some transformations for pictures. So let's go back to the original box. So let's try to create some transformations. So I'm going to create a picture that takes or a function rather, that takes a picture and produces another picture which is turned. And I'm going to exploit something that's called functional composition. So functional composition is when you have a function from A to B, and you have a function from B to C, I can sort of compose those into a function from A to Z, like this. So in my case, I'm going to have a box-to-box function, and I can compose that with a function from a box to a rendering. And that's going to produce for me a function from a box to a rendering, because in this case, A and B are the same. Now, a function from a box to a rendering obviously is, well, it's just a picture. Which is kind of strange. So I can sort of compose something with my picture and create a new picture. But that's what I'm going to do. So I'm going to create something called turnbox and compose that with my picture. Of course, I don't have this function yet. So turnbox is going to be the function that turns my box. And a box is just these three vectors. So I sort of pull the box apart. And then I'm essentially going to do what I did by hand earlier on. So I'm going to manipulate the A vector, which is where sort of the first arrow points to. And I'm going to change this so that my new B vector is going to be the old C vector. And this is going to, yeah, I suppose I need to show this as well. So I have this vector type, which is just X and a Y. And I can sort of do vector arithmetic. I can add vectors, then I can turn it. I can negate them so it goes the other way. And that's a lot of words, and let's see if it works. So I'm just going to drop the box and see if I can turn the fish. Well, now you just see the turned fish, so it's maybe you don't remember that the original fish looks like this. And the turned fish looks like this. And you know, the twice turned fish is going to look like this. And I suppose, you know, you can keep going like this, right? So, but all I'm really doing is turning the box just before sort of passing it to the fish picture, the original fish picture. And, well, okay, so that's the first transformation, and this is going to have to go fast. So, this is the wrong thing. I'm going to create two more sort of simple transformations like this. So, flip is going to take the original picture and flip it like this. And again, I'm sort of going to transform the picture by transforming the box. So I'm going to have a flip box. Flip box again is going to be very simple. Let's see, flip box. Again, move the A vector. Just turn the B vector around and leave the C vector as it was. Now I have flip. Well, again, to see what's going on, suppose you need to see the original fish. Then you need to see the flipped fish. Of course, what happens when I flip the fish twice? It's the original fish because, yeah. Okay, so third simple combinator. This is a little bit less simple, but not that much. This is called toss, which resembles tossing the fish up into the air. But it's the same mechanism. So I'm tossing the box, and then the fish sort of has to follow because that's what a fish does. So, okay, toss box. Oh, yes. And this is more complicated now. So I'm going to start at the A vector, but then I'm going to scale by a half the result of adding the B and C vector together. And I'm going to show you how this looks in practice. So this is vector math thing, don't worry about it. The B vector is going to be the same thing that I add to the A vector. I'll try to explain real fast because we don't have much time how this really works in practice. Now sub is taking the original, the first vector and then subtracting the other vector. Let's see. Maybe we should, yeah, we can just toss the fish. And then we can draw both the original box and the tossed box here. And maybe it makes it clearer what's going on. So I start with this box, and then I throw it up into the air, and it sort of shrinks a little bit. And, well, that's where I go when I go from A, and then halfway from the sum, well, the sum of adding B and C together. And, yeah. So now I threw the fish up into the air. Nice. That's the third and final sort of simple transformation. I'm going to try to start to compose pictures. So taking more than one picture and producing a single picture from those. Okay. And the first thing we're going to do is something called above. So I'm going to put one fish on top or above another fish. And I'm going to have a sort of a generalized way to do that. So I'm going to assign a ratio to each of the fish. So maybe one fish gets more space than the other fish, or the other way around. So these m's and n's are sort of weights that I give to the two pictures that I'm placing on top of each other. Okay, let's see. I said many times that a picture is a function from a box to a rendering, so I'm going to produce a picture by writing a function from a box to a rendering. So here's the box. And I'm going to calculate the amount of space I'm going to give to the top picture, which is going to be my factor f. So I'm giving it a weight, and I'm sort of, m is going to be the amount of space for the first picture, and then I'm dividing that by the total weight, and then I can, well, let's see. I'm going to split the box vertically. So take your one box and then split it in two, like so. And then once I have these two boxes that I can put my fish inside, I'm just going to sort of apply them like this. Because, you know, pictures are functions that you can pass boxes to get a rendering. And a rendering is a list of stuff, so I can sort of, if I have two renderings, I can add them together just by putting the lists together. That's my rendering. Of course, I don't have split vertically. And how much time do I have? Oh, man. OK. I'm going to start cheating now, OK? OK, so split vertically is taking a box and splitting it. It relies on, well, this is the outline. That's no good. So I'm going to cheat for remove vertically as well. And what I'm doing, well, all I'm really doing is taking one box and producing two boxes from them. But I don't have time to sort of write it all nice like this. Let's see, cheat, split. Oh, not split, I have split. Scale vertically. Like so, let's see if it works. Above ratio is implemented now. And since I have above ratio, above is really simple because above is just sort of a fair above ratio. So give the same ratio to each. I can do that by calling above ratio with 1 for each picture. So I use partial application to get my above function. OK, let's see. Above, fish, and fish. Does this work? I'm going to hide these boxes. Works nicely. I'm just going to very fast sort of show what's going on underneath the covers here. So there's nothing more or nothing less than splitting the original box in two boxes and then putting the fish inside. Similarly, I'm going to have beside, and I'm really going to cheat for beside. Let's see, cheat, beside, ratio, and yeah, it's the same thing here. I wish I had written a sort of more powerful cheat. Let's see, move horizontally, scale horizontally. I'm programming really fast, aren't I? So I no longer need these boxes. Okay, so this is putting things beside each other. Exactly the same principle as above. Now, the cool thing is, once I've done this, I've been manipulating boxes for a long time, but now I don't sort of have to do that anymore because I have these powerful things. So next thing I'm going to do, that's beside. I'm going to implement quartet. And quartet, give me the outline, is going to take 4 pictures and produce sort of a 2x2 grid. So it's going to look like this. All I really need to do is to take these pictures I call sort of northwest, northeast, southwest, southeast. I take 4 pictures and produce a single picture by sort of putting them next to each other and then above each other. So let's see. Yeah. And I mean, these are all pictures. I just have to do this. I'll try to go real fast. Let's do. I'm going to, let's see, that one's right. Should I be spending my time doing this? I'm not quite sure. Oh, it's more like this, right? Yeah, I'm getting somewhere. So I'm turning this flipped fish around sometimes, and I did it the wrong way. Yeah. Is it like this? It's a nice circle, yeah. And I just wanted to show you that once you have this, you know, I can. It composes so nicely, right? Like this. Oh. Because all of these are just pictures, right? So I can. Ooh, it's very nice. Okay, I'm going to create something called a no-net, and you're accustomed to me cheating now. What I'm doing here is producing a 3x3 grid, so it's very similar to a 2x2 grid. I'm not even going to demonstrate it. I'm going to use it later. More interesting, I'm going to create something called over, which basically just puts 2 fish inside the same box. So how do we do that? Well, it's very similar to above, really. So sort of a degenerate above. So you don't produce new boxes. You just put 2 pictures inside the same one. Now, what happens if you put the same fish on top of itself? Well, it's just the one fish, right? Not very interesting. But 30 seconds? Are you kidding me? Okay, this is a problem. More nice, yeah. Okay, so I'm going to produce some tiles. I'm going to have to cheat for that one. What? That's not correct. Let's see. Cheat t-tile. So t-tile is one of the components we need to produce the square limit. And what it does, it takes one fish and then sort of does some things and put everything on top of each other. I'm just going to show you how it looks like. And I'm going to hope they don't stop me in 3 seconds. Because I'm really quite soon I'm going to be there, right? Oh, this is rushed. Let's cheat with another tile that I'm going to use for the final. So this is similar to the t-tile. It replaces the one big fish with 2 smaller fish, like so. And all I'm really doing is take one picture and sort of rotating it and putting everything inside one thing. So now all I have is 3 small functions left. That's where the recursion happens. So if you have like 2 minutes, maybe 3 minutes. I'm sorry about this. I will cheat so it goes fast, right? So what a side does is going to be one of the sides that sort of grows into infinity, right? So it has a degenerate recursive case in which it's blank. And then if it's not blank, it's going to be a quartet of calling itself recursively and then having a t-tile. We'll see what that looks like. Now, if n is 0, it's very boring, it's the blank picture. But then it grows as you sort of give it more to work with. So these are the 2 t-tiles, the original t-tile and a turned t-tile, and then 2 blanks on top. And then you can sort of go on like that. You can it sort of accumulates sides up like that. And similarly, so much cheating today. The corner, it's sort of similar. Blank in the degenerate case, then you call itself recursively, and then you have a side and you create another quartet. And we'll see what that looks like. So, corner 0, the blank picture, corner 1, a single utile, corner 2, another utile on top, and then a side and a side. Corner 5, nice recursion. And then we have all we need to sort of produce the final, by cheating, square limit. And this is just calling these functions. So it's a utile, a corner that you turn various degrees of time, side that you turn various degrees of time. And then you have this 3x3 grid that sort of used to compose everything. And then you have something that looks like limit. Well, let's do 4. And it's done. So really sorry for going over time. It does take time to sort of implement this, surprisingly. But of course, if you didn't understand basically anything of what I was doing, but sort of thought it was cool, I have a workshop that it's possible, which goes much slower. I mean, this takes like maybe 2 to 4 hours, depending on your sort of familiarity with functional programming, stuff like that, where I sort of do it very step by step. And you can sort of go through it. So that's called Escher Workshop, and you can find it on my GitHub. So thank you.